In this slide, we will learn about the Newton's method. Newton's method actually is different from the gradient descent method in the sense that it also uses this second derivative as the information. So if you remember, we had this search direction sk, and in the gradient descent, we had the function derivative, the first derivative of the function at the kth iteration. In the Newton's method, we also use the second derivative as a division here. But this second derivative, we will have multiple derivatives if we have more than one variables. So based on x1, based on x2, also based on x1 and x2, we have partial derivatives. That's why we call this as Hessian, or we can show, for instance, for example, two variables, x1, x2. We will have a derivative, the second derivative f2 xk is equivalent to, we call this Hessian matrix, and this becomes partial derivative of f and del x1 square, second derivative, that's why it's square, and the actually partial derivatives for x1 and x2 are the diagonals, and the other sides are again f, but at the denominator we will have delta x1 and delta x2. Here also delta square f divided by delta x2 and delta x1. So there are four derivatives that we need to take for just the second derivative, and that gives us actually the gradient here, fxk, and as the denominator we have the Hessian function xk, Hessian matrix actually. So this is for two variables, and if we increase the variable number, so the diagonals will be always the individual derivatives. For 3, for instance, this will be 3 by 3. For n variable, this will be n by n. So there are many variables, and the search direction for the new point will be the current point xk minus the step size and the gradient fxk divided by Hessian xk. And in here, so Hessian is a denominator, so that's important. It doesn't have, it shouldn't be 0. Also we can write it like as the inverse matrix at the top as the denominator here. Then xk plus 1 is equivalent to xk minus alpha minus minus is here, we make this plus and put the minus inside, Hessian inverse xk and gradient f xk. It doesn't matter to be here or on x, it can be like this. Okay, taking this inverse can be problematic, that's why we need to be careful. But this method is less sensitive to initial point and step size alpha, and usually we use alpha equals 1 in general. We don't need to try different values. This is good for Newton's. The reason of having less sensitivity is because we are using the second derivative as additional information. The more information you have, the better you go to the faster you go to the optimized point. So that's why this is less sensitive, because we are using additional information as the second derivative. But the problem here is that, so this is the advantage, let's put as a tick. The disadvantage is that h is sometimes impractical or difficult to calculate. Also, another advantage is again based on Hessian, especially for higher number of design variables. The inverse h-1 is impractical or difficult. So we have to be careful about this H-Hessian matrix. But again, it is very efficient. As long as you calculate these, it's very quick and efficient to go to the optimum point. It doesn't, it is not dependent on the step size and initial point, like unlike the gradient descent method. In this slide and onward, we will have an example, example 2, with this function with two design variables, and we will use to solve this optimization problem, minimizing it, using gradient descent as well as Newton's method to see the differences and advantages of each. Also, we will try some different step sizes, some initial points. We will try to solve using these. I will not show the analytical solution, but show the graphical solution only. So you can write some MATLAB codes to be able to make this optimization problem as a coding procedure, let's say. In here we have a contour plot of x1 and x2, and actually these circles show some increasing or decreasing hills, and this is the minimum point. And we started from here 15 to 15 here, you can see. And in the first step we will move here, and the step size is 0.1 for this case for gradient descent. So it moved here in the first iteration or second iteration maybe. Then moves here, then moves. As you can see, when it's getting closer to the optimum point, the movement is getting slower. So that's the disadvantage of the gradient descent. One option to be able to make it faster can be increasing the step size in a certain magnitude when we get closer to the optimum point. If we don't see any divergence, so this is, we see here convergence, for example, coming here. That's why we can maybe increase the step size slightly to go faster. But if we use constant step size, this is, here there's constant step size, the derivative information is getting smaller. That's why this is getting smaller actually. So after certain iterations, you can see it's getting very small and small, but reaching to the optimal point. So this is the zoomed in version of the image, as you can see. And after 36 iteration, we obtained a convergence of the function value, and we obtained the minimum of this function. So let's check a step size of 0.2, because we saw that it is small enough because it's converging. Maybe increasing it can be advantageous. We keep the same initial points. So when we increase this to 0.2, you can see the jump is more. It is much more, getting much more, and it's diverging actually. So the derivative doesn't help us because the step size is very effective here. So increasing it to 0.2 at this location didn't help actually, and it diverged. So too much divergence, we will never be able to get the minimum point, and it didn't converge. So another trial is that, okay, step size is 0.2, maybe the initial point, if we change it to a closer point to the minimum, then we can have a convergence. So we change this from 15 to 0, 0. Let's check. We started from here, and the minimum is here. It's very close to minimum actually this time. 15s were very far away. But in this case, you can see 0.2 step size was okay, and it was able to reach at 6 iterations to the minimum point. So you can see the importance of initial points and as well as the step size for gradient descent in these problems, in this problem. So let's use this example too with the Newton's method. And in the Newton's method, we will check if we will set the step size as 0.2. As actually we said while talking about it that step size doesn't matter, so we can just use 1. But I want to show you how it changes the results. So we started from 15, 15, and step size is 0.2. If you remember, the gradient descent actually diverged in this case, didn't converge. Let's check this. We start from 15, 15, minimum is here again. As you can see, it goes very well because it's using the second derivative as well as the information. It goes to the point as expected and find the solution in 29 iterations. So it doesn't diverge. But this is still too much. Maybe this small step size was the reason of this. Let's check step size 1 or 0.5 first. So we can be maybe worried about like divergence here, but as I said, Newton method is using the second derivative, so let's don't worry increasing the step size. Again, we start from 15 to 15. You can see it goes to the minimum point, doesn't diverge, and went faster because the step size was large. In 11 iteration, we were able to get the minimum point. Then we will use the default alpha value 1, and again starting from 15 to 15. In here, you can see that we start from here, but in the first iteration, like in the first estimation, we were able to reach to the minimum point. So this was very, very effective. And that's why in one iteration, we were able to find the minimum. So this Newton's method is very effective if we use like a regular step size of 1 as default, and initial point may not matter. You can try different alternatives by writing your own MATLAB code and see how it works with different initial points as well. So as final comments, I want to talk about some MATLAB optimization toolbox functions that utilizes these gradient-based optimizations. First of all, you can use fminunc function in the MATLAB optimization toolbox, which is an unconstrained optimization function. If constraints exist, and in this case, advanced gradient method-based methods should be used with constraints, including penalty function methods. This is not the topic of this class, but you can get some more advanced class for these to learn these. But still, you can use the MATLAB optimization toolbox because it has this fmincon function. You can just simply use it by calling it for a constraint optimization as well. So we have gradient-based methods, as we said, in these functions. The problem with the gradient descent methods or gradient-based methods, actually, it can trap in local minima if the function has multiple local minimums. We mentioned this before as well. So here you can see multiple minimum and maximums. So if we start from here, for instance, it will trap is in here if we are trying to find the maximum, finding the minimum. So this is the global actually. If we start from here, for instance, it comes here to the minimum and stuck here. It doesn't go further because the derivative becomes 0 here anyway. So that's the issue of the gradient-based methods, trapping in the local minima. So relative minimum is also global minimum, it says. So basically it considers that this is the global. It doesn't understand that there is further further global minimum. What we can do is we can change the initial point, for example, to here to see if there is any other minimum. So we can start with different initial points, try different points to get a result. And also global search algorithms are used to overcome this issue, such as genetic algorithm, particle swarm optimization, simulated annealing, etc. These don't use gradient-based methods, that don't use any derivative information, but different other advanced algorithms. You can learn about these in a further advanced class. This is they are not the topic of this class actually. So if you are interested in these, you can check this book of Rao, Engineering Optimization Theory and Practice, to be able to have some information about these. Finally, if we want to revisit the structural optimization categories, now we can use these gradient-based optimizations actually for these different alternatives. Usually gradient-based optimization is used for these, And you can, for instance, use the MATLAB optimization toolbox as well, like fmincon, with some constraints for size optimization, shape, and topology optimization as well. There are freely available codes for these, and in my computer-aided design class, I'm also teaching topology optimization in MATLAB, so you can go and check my YouTube videos on this topology optimization to be able to learn how to, optimize a structure topology using MATLAB, for instance. That's pretty straightforward, and please go ahead and check and see if we can use it in MATLAB actually to get some optimized structures. And thank you very much for listening. This is the end of this section, and see you in another class.